Welcome to Careless Coder. Today lesson 11 of Commodore 64 assembly sprites. Motherfucker! Oh, it came into my mouth and it tastes horrible. Ugh. Ugh. Whatever happened to 7-Up? 7-Up was so much better, but you don't see that over here anymore. Oh my god, this stuff is sweet, and this is even 0 sugar. Ugh. Yeah, I don't like Sprite, but I love a sprite on the Commodore 64. So let's create a sprite, put it on the screen, and make it move. And make it collide with another sprite. I don't know how to get rid of this. If I pour it in the sink, I probably commit an environmental act of terrorism. That's how bad this stuff is. Yeah. Okay, let's jump in. So we first draw our sprite. I use this online sprite editor, which is really great. It also allows you to make multicolored sprites, but we will use a single color sprite because that's a nice, big, massive sprite of 24 pixels high. Now I let my artistry do all the work here. And then we have a ball with a nice highlight. We center it. And then we export it. Where is it? Where is it? Where is the export? Oh, there. Yes. No. Yeah, there it is. And we export it as bitmaps to raw byte stream. And you just copy the contents that is generated and paste it into Kick Assembler. And then we need to change capital byte into dot byte with smaller case. So now that we have the sprite drawn in this awesome online drawing app, a little bit of background about sprites. We have 8 sprites on the Commodore 64, which is not a lot, especially for games, for example. You would generally use about 16 of them if you have your missiles and your players and your opponents. So how did they do that? Well, they did something called sprite multiplexing. So basically they put raster interrupts on certain lines and then redraw the sprites or reuse the sprites when the other ones were already drawn. Now there is a bit of a problem with that is collision detection. That goes out of the window. We will be using collision detection to see if 2 balls are colliding. We're not going into sprite multiplexing because that is a rather complex subject and code gets very long very quickly. Maybe in the future I may do something with that. I only did it a handful of times myself and it was always very tricky to get working without flickering. So yeah, let's put a sprite on the screen. So what we will be doing is iterate through a program in a couple of iterations that we will finally end up with 2 balls on the screen that move independently, and when they collide that they will change color. But first we need to get a sprite on the screen, period. So what I did is I copied the code from that website and I changed byte capitals into dot byte lowercase to satisfy Kick Assembler. Now we need to load actually this location into a sprite pointer, and I want this to be on location 2000 because that is a nice available address currently. And let's do that basic upstart to main. This is Kick Assembler that basically creates that basic code that will automatically run your application. And to main. Now where do these pointers live? Well, they are always at a certain distance from your screen RAM. Now at default your screen RAM is on 1024 decimal and they always live 1016 bytes above that. So if we go here, we do 1024 plus 1016 is 2040, which is in this case address 7F8. So this is
sprite pointer 0. And 7F9 is sprite pointer 1, 7F A is sprite pointer 2, etc., 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 until you had all 8 sprite pointers. We only have 8 sprites in the Commodore 64. So we can say now, let's set 7F8 to point to this address. Oh, store 7F8. Now, which address do we need to put in here? Because this is an 8-bit value. Well, basically that is also a bit of mathematics. Each sprite page, I call it a sprite page, don't really know what the correct name is 40 hexadecimal bytes. So if you put 0 in here, it will live on 000. If you put 1 in here, it will live on 0040. If you put 2 in there, it will be 80, etc., etc., etc. So basically, we want to have it on 2000. So 2000 divided by 40 is 80 hex. So we will load 80 hex in there and set it to 7F. And yeah, we don't know where it is. It could be anywhere on screen, maybe even on an invisible location. So let's set XY position for sprite 0. Now the locations start at D00. So D00 is X and D001 is Y for sprite 0. For sprite 1, X is at D002, Y is at D003, etc., etc., etc. So it just continues counting on. So let's put it on the center of the screen, which is 80 hex. Store D00 there and store D001. Let's jump infinitely. So you would think, well, we're there. We should have a sprite on the screen. However, let's run and see that we're still missing something. It is running, but we don't see the sprite. We have to enable the sprite. Now there is a single byte that allows you to enable them, which is D15. So in this case, we only want to enable bit 0, so LD1. So now we should have a sprite on the screen. There we go. We got a white ball. And if you have black balls, that is perfectly fine. Yellow balls, we do not discriminate over here. Except when they turn blue or green, you may want to see a GP. So let's make this ball move across the screen. So in order to move that ball, we basically have to just update the D00. So if we do that, increment $D000, right, it should run across the screen. Let's test that hypothesis. Something is wrong. Why? D00, that. Oh, I see. Now it should jump across the screen. But it does it so quickly, faster than the ray gun is actually able to follow it. So what we need to do is we have to wait for a certain raster line. Now we could use a raster interrupt. That's what you would normally use. See lesson 10 for those. But we're just going to do it quick and dirty. We will check for line 255 in the D register, because this is a demo just to learn. Compare D12, that is where the line is, the current line is being drawn. And then we branch not equal to 3 bytes back, so we keep comparing what is in D012, and when it hits 255, then we increment the position. So now we should have a ball that is migrating slowly across the screen. And there we go. But there is a little caveat. It only stops here. Now, why is that? Well, the astute of you will have realized that D000 is an 8-bit value. And there's more than 255 positions here. Okay, so let's fix that by seeing whether this D000 is overrun. So the carry is set. So instead of just using an ink, let's use the accumulator, because then the the carry bit is set. Let's also clear the carry. And then we just do add carry 1. So basically we still have the same thing now. This should just work the same. Let's prove that. And I need to store it first, otherwise it doesn't do anything. All right, let's prove it. Yeah, so this still does the same. But now a carry is set, so if the carry is set, then we say toggle high bit sprite 0, and otherwise we jump to wait line. Already put a label there for that purpose. So let's toggle that bit. Well, that is, we need to read D10 because this is the register that has the 8 bits for the 8 sprites to see whether its position is higher than 255. So basically adding 255 to that sprite position. And we just need to toggle it. And the easiest way to toggle a bit is using an XOR. 1, 2, 3, 4, 5, 6, 7, 8. So we're just toggling this bit. Now usually you would create a function for this where you store this value in a memory location that you update before you toggle the bits. But that is the drill. You already know that if you did the other 10 lessons. Oh, and then we need to store it to D10 again. And that should still work. Yeah, and now we should actually have a ball that moves all the way across the screen. Oh, already loaded. There we go. Yes, there we go. Now we can actually show that it is toggling by incrementing the color of that sprite. The color of the sprite is D27 for sprite 0, D28 for sprite 1, etc. So you see, as soon as it hits that boundary, it will change it, and here at the 0 position as well. And now it's the same color as the background. There we go. Okay. Right, now let's give this ball a friend, because usually they come in pairs. So we know 7F8 is the sprite pointer 0. So 7F9 is sprite pointer 1. And we're going to point it to the same sprite. We can just do that. And we need to enable them. So we have now sprite 0 and sprite 1 enabled. So that is value 3. And let's put it on a position of 60. So like we said, we just continue to count on. So X is D002 for sprite 1. And Y is D003. So let's show we should have an extra sprite on the screen. There we go. Hey, it's pointing to something wrong. Right. I set sprite 7F. And there you saw that that little block. That is uninitialized sprite memory. So, yeah. Okay, let's make them a bit of a Christmassy color. Let's set colors 5, store in D027, that is the color of sprite 0. Alright, and now we should have a lovely red and green pair. That looks like the balls on your Christmas tree. Alright, let's make this red ball move independently up. Let's be a bit dodgy. Let's copy this code. Like I said, you would usually create a function where you have this bit mask to toggle which bit as a variable in memory that you would then set and call this function. But this is demonstration purpose, so this is perfectly fine. And it's really, really quick as well. We're not going to jump to a weight line here. We're going to do that there. Here we're going to jump to sprite 1. Let's make this sprite 0 just for clarity's sake, so we know that we're moving. All right. Sprite 1. Yeah. And we're going to move it up. So we now need to set the carry so that when we move D000, D003 through 0, it will actually clear the carry bit. So let's load that Y position. Let's move it a bit quicker as well by subtracting 2 pixels from it. We need to store it back. And now the carry may be cleared. So if the carry is cleared, then we will actually jump to toggle high bit 1. And otherwise we jump to wait line. This should work. Last famous words. Yeah. And you see it moves quicker than the green ball. Now every now and then they hit each other. And usually when balls collide at a high velocity, they tend to change color. So let's do that. And it is really simple in the Commodore because there is collision detection on sprites. There's interrupt-driven collision detection and polling-driven collision detection. And we're going to use the polling collision detection because we're already screen-bound here anyways. So that will be perfectly fine. Now how do we do that? That's really rather simple. We can actually read the register D01E. And the byte in this memory location will set the bits of the sprites that are currently colliding. So in this case, we only have sprite 0 and 1. So when they collide, they will both be set. So the value will be 3. So we know that if it's not equal, so not 0, then we need to change color. Increase sprite colors. So this keeps looping. Let's do another loop here. And let's really increase sprite colors. Well, we know the drill. D027 and D028. And that will change the colors as soon as they hit. Why is this it's already defined? Oh, yeah. There we go. All right. Now it should hit the following run. Boom, there we go. And they change color. And as long as a pixel hits, that's why you see it flashing, it will trigger that collision detection because they're basically still have overlapping pixels. So in a game you would just, as soon as it triggers, you will disable a sprite or move the sprite. But this is how simple sprites are on the Commodore 64. It's really quite powerful. And now it's invisible because it's the same color as the background, but it still is there.
So there you have it. We wrote a series of iterations to put a sprite on the screen, then move it completely across the screen by toggling the high bit, and then we introduce another sprite and we let them collide and change color of the sprites. And as you saw, it's literally just maybe 50 lines of code to do something as complex as that. And that is really, really fast as well. So yeah, sprites are very useful in Commodore 64. So I promised also one more lesson, and that is the joystick control, and I think we will use a joystick to control a sprite, because generally that is what you do. So I hope you learned something, and I hope to see you in the next one.